My name is Adam Smith from Nobel Prize Outreach, one of the outreach arms of the Nobel Foundation based in Stockholm. On behalf of us all, I'd like to welcome you to this conversation with Venki Ramakrishnan, which is part of our long-running collaboration with AstraZeneca, the Nobel Prize Inspiration Initiative. The initiative is designed to take Nobel laureates around the world to meet the next generation of scientists. So, Venki, welcome. And this is an interesting time for you. I mean, obviously, everybody's totally disrupted. But for you, this should be a return to normality after 5 years as president of the Royal Society, back at the MRC LMB and able to get on with work as normal. First question,
Yes,
is it a relief to you to be out of the public gaze at the Royal Society?
Well, it's certainly a lot less hectic, and I have more time to think about where we want to go in research. I should say the 5 years were fun in that they exposed me to things that I would never have experienced otherwise. You look at science from a sort of 30,000-foot view. How does the scientific enterprise work? How is it funded? How do you make the case for science? How do you make science inclusive? What is wrong with science culture and how can we fix it? International relations, the whole host of things that as a working scientist, you sort of take for granted or you don't think about. And I think being president of the Royal Society meant I was thrust right into the middle of all that and had to think about it on a day-to-day basis. So that part was fun, but I'm also rather happy that it's come to an end. I think, you can only take so much of that. And I'm primarily, I think of myself as really a sort of lab scientist. And so I'm now full-time back in the lab, but I'm also working on another book. So that's going to keep me busy.
Mm. And of course, you work at the legendary MRC LMB with this wonderful atmosphere. How much is the current situation of people having to be careful about associating with each other disrupting that magic of the place?
It is very disruptive. So the lab is open, but we don't encourage everyone to come in at once. We try to, we don't enforce the number who can come in, but it's sort of groups decide what days they will come in and do bench work. We have to stay 6 feet apart. We can't talk to each other even while wearing masks, which is required everywhere except in my office, as you can see. So it's a very arduous way of working because one of the reasons the LMB has been so successful is the spontaneous conversations we have, often in the canteen, which is now closed. So it's better than not having not being able to do work, but it's nothing like a sort of normal modus operandi.
Yes, because science is such a social enterprise, and the LMB is organized so that people will bump into each other and chat. So it must really be very difficult. Okay. As Anne mentioned, you made this transition from physics to biology, which of course is following the footsteps of many famous physicists and indeed physicists associated with the LMB, Francis Crick, for instance.
Yes.
Was there a moment when was there something you saw that really changed how you wanted to live your life?
I think there was a bit of push and a bit of pull. The push was that I found I wasn't really that excited about what I was doing in physics, and I couldn't see a way forward. And by the end of my graduate school in physics, I really didn't feel like I was thinking like a physicist should be thinking. And physics is also, if I'm rather blunt about it, it's a very mature field. And it's really hard to make big fundamental breakthroughs in physics. On the other hand, when I was in graduate school, and I noticed every issue of Scientific American had some major breakthrough, or the other end, all sorts of things, immunology, cell biology, memory and neuroscience, structures of molecules. And it seemed as though these things could be done by mere mortals. You didn't have to be an Einstein or somebody like that. And so I thought of, that since the field was sort of taking off, or had been taking off for decades, but showed no signs of stopping, that it was a good time to train to be a biologist. And one reason I went to graduate school is I didn't know any biology. I was actually offered a postdoc at Yale. And actually, one of the people who offered me a postdoc was Tom Stites, which is something of an irony considering how things turned out. And the other was his colleague, Don Engelman, who used to collaborate with Peter Moore. But I turned them both down because I felt I needed to go to graduate school and learn biology. And I even took undergraduate courses in my first year there, even though I had a PhD. And I always tell people, if you're switching fields, you cannot be too arrogant. You have to have the humility to start from the beginning, because in your new field, you're a nobody. You don't know anything. So,
yeah, it's difficult because everybody tells you as a graduate student, you've got to become an expert in this quickly. And to then sort of turn around and show that you're not an expert in things, you need some confidence actually to be able to do that, to be able to show other people that you don't know.
yeah, possibly, or well, you could think of it as insecurity too, that I needed to be sort of taught these things. But yeah, maybe you're right. But whatever it is, I never regretted those 2 years. I think they really gave me a broad foundation in biology that's helped me throughout my career. If I'd done a postdoc straight out of my PhD, what I might have done is learned quite a lot about a very narrow slice of biology, and I wouldn't have that broader context in which to work in.
Sure. So Rachel from EMBL wants to know whether your term as president of the Royal Society has changed the way you behave as a lab head.
I don't think so. My attitude has always been I'm not a micromanager. In fact, I don't choose projects for people. I tell them what the open questions are in my field and what might be feasible, and ultimately each person in my lab chooses his or her own project. And once they choose that, I give them, I don't sort of stand over their shoulder, and I encourage them, but they feel vested. It's their problem. They're working sort of in my lab, but it's really their problem. They own it to a large extent, and I think that has meant that people really, if you feel ownership in a problem, you give it your best shot. And also, if you picked your problem, that means you're sort of really interested in it. I think that very simple recipe has worked. I'm not sure I learned anything in the 5 years about sort of the big picture of science that really changed much about how I run my day-to-day lab.
Does the current situation, do you think, with people now focusing a great deal more on science? I mean, we understand that the pandemic has created an environment in which people are listening to scientists and science in a way that perhaps wasn't happening before. Does that change, do you think, the responsibilities of the scientist to be more to have more of an outlook towards the public?
I think it works both ways, and I think the pandemic has really brought out some of the best features of science. Scientists from all over the world would often drop the problem that they were working on and then sort of pivot towards COVID and used the expertise that they had in many different fields, from material science to epidemiology and virology. So you had the whole range of scientists, mathematicians, epidemiologists, etc., all swinging towards what could they do to help with the pandemic? And it's been fantastic. From that point of view, science has never been so much in the forefront. Now, it does reinforce a message, though. We do it now because of the crisis. What happens when the crisis is over? Well, my feeling is scientists do have a social responsibility because much of our work is funded by the taxpayer. And so you ought to be able to tell, a truck driver or a farmer, why is some of their taxes, why is it okay to use some of their taxes to do your work? Okay. And if you can't do that, then maybe you shouldn't be doing what you're doing. And I don't mean by doing that you should only be doing applied work or work directly related to infections or cybersecurity or something of immediate concern. It is very easy to make the case that fundamental science, fundamental biology underpins almost everything we do. And if you look at the pandemic, Fred Sanger had no idea that there'd be a COVID pandemic when he figured out how to sequence DNA, which then led to better ways of sequencing DNA, which led to rapid sequencing of the coronavirus genome, which led to test kits for infection, which were based on PCR, which, somebody fooling around with bacteria growing in thermal hot springs in Yellowstone, isolated enzymes, which are the sorts of things we now use in PCR. So you can see how there's this interconnection between curiosity-based science and eventual application. So I'm not trying to say scientists should be constricted in what they do, but I think they should bear in mind that if what they're doing can be useful, they ought to make that at least clear so that other people can put it to use if they don't do it themselves.
Mm-hmm. Thank you very much indeed. I suppose another thing that the pandemic has highlighted, which all scientists knew already, was that science is an international business. In your own case, Marina wants to know, how did science differ for you, doing it in the US and now doing it in the UK?
It's perhaps a slightly unfair comparison because the LMB operates in a not very common way, in the sense that we're a research institute, we're centrally funded by the Medical Research Council, primarily 80% of our funding comes from there. And so we have very stable funding. We're not allowed to have large groups, but because our funding is stable, we can take on very long-term problems. And part of the tradition of the LMB has been to encourage people to tackle truly important problems, no matter how challenging or long-term they are, as long as you can make steady progress towards a goal. It's not as if you can hang around for 5 years and do nothing. That's not going to be acceptable. But they'll understand if you're working towards a long goal and you're not making breakthroughs all the time. Whereas in many universities, including the US, but that's also true in the UK, you have to rely on 3 to 5 year grants, which means by year 2 or 4, you have to have a steady stream of output to resubmit your grant for renewal. And that encourages a kind of incrementalism or short-termism. And it's, I think, a bit unfortunate. And this is part of the things that scientists are grappling with, how to encourage both types of science. You can't have everyone doing very long-term science. I don't know if that's necessarily good. I think what science needs to be is a broad ecosystem where you have all different types of science, some doing very long-term science, some doing immediate applications, and everywhere in between. And that's a healthy ecosystem, a diverse ecosystem. Just like with any other ecosystem, you need diversity. You need this sort of diversity of approaches.
But then this begs the question that, as you describe in the Gene Machine very beautifully, you pursued a 30-year search for the structure of the ribosome. And how do you pursue a 30-year search, much of it done, as you said, in the US, in an incremental way? If you've got a long-term goal,
it's a hard,
you've got
it's a fair question, and there's no straightforward answer. But I would say, it's not. I mean, the LMB has no monopoly on long-term challenging projects. They've been done in all sorts of environments. I think the LMB makes it easier to do it, but people, as you know, having interviewed Nobel laureates every year, people come from all sorts of institutions and have done tremendous work. And I think if you're in a place where you're dependent on a sort of renewable 3 to 5 year grant, what you have to do is figure out how to break up your problem into feasible steps, where at the end of each step, you have a sort of progress report that's convincing, and the panel can see you're headed somewhere, but you haven't wasted your time, you've actually accomplished things. So I think breaking the problem down into sort of bite-sized pieces is really key to success. And it's key to success here also. We get reviewed every 5 years. And so we do have to show progress. And I liken it to, if you wanted to climb, K2, for example. I choose K2 because it's much harder than Everest. Many more people have died on K2. If you wanted to climb K2, you wouldn't sort of plan, okay, I'm started off and now I'm going to keep going until I reach the top. That's not how it works. You have to figure out all of the stages and how to get to the first stage, and then from the first stage, how to get to the next stage. And, in each stage, you have to sort of stop and take stock, and you may have to change plans along the way. The path you were planning to take might not be feasible. So it's very similar, I would say, to that sort of enterprise.
Mm-hmm. And every so often, your path gets derailed a bit, and questions are flooding in. Sumanit wants to know how you coped with the disruption caused by the Nobel Prize Award in 2009, and what that did to research.
So I will tell you, a member of the Swedish Academy of Sciences, whom I know quite well because he's in the ribosome field, Anders Liljas, and I actually described this in the book. He once told me, this is before I got the prize, he said, the Nobel Prize is a kiss of death. And what he meant was that as soon as you get the prize, you get invited to all sorts of things which you would never have been invited to before. And, human beings, it appeals naturally to your sort of vanity. You feel flattered and you say, okay, that sounds like a good idea. And before you know it, you're on the road all the time. But I was pre-warned about that. And I was also warned by another very well-known Swedish scientist, Gunnar von Heine. And he said, you should check out this guy, Rod McKinnon. He's sort of ignored all the hype and just kept on beavering away at his, ion channels. And I sort of decided to take that path. So I did do a few events that I wouldn't have done before. But if you look at my publication record after 2009 to the sort of 10 years from, well, maybe not 10, but say certainly 5 years before 2009, then it's just as good. And so I would say you just have to ask yourself, what is it that you want to do? And it also depends at what stage do you get the Nobel Prize. Many Nobel laureates get it when they're long past their prime. They're in their sort of mid-70s or 80s, and they haven't really done sort of first-rank work for quite a while. And then they suddenly get the prize, they're in their limelight. Then they have a choice. They could become ambassadors of science. They could go around talking up science, encouraging young people, perhaps writing books. So there are many paths you can take after the Nobel. But if you're an active scientist, as I was and still think of myself as, then, you have to be fairly rigorous about saying no.
Mm-hmm. Well, yeah, no, you clearly have the self-discipline to avoid what you in the book call Nobelitis.
Yes, that's right.
And you mentioned there's a precondition of Nobelitis, which is the disruption caused by expecting the prize.
Oh, that's a dreadful thing, and that I have to say, I've had arguments with Swedish Academy members, not before I got the prize, because that would seem a bit like sour grapes. But it would be as if I was anticipating not getting it and complaining about it. But after the prize, I did point out that this rule of three is it's not clear that it makes sense in today's science, and let me tell you why. When the Nobel Prize was instituted in 1901, scientists hardly communicated with each other. There was certainly no internet or anything like that. People would meet once every few years. You look at the Solvay conferences in physics, they were once every 5 years or so. And so what would happen is somebody would have an idea, they would have quite a lot of time to work on the idea and do a body of work. Then they'd come and present it at this meeting. There was no question who had done what. Okay. But now what happens is you go to a meeting and you have just the germ of an idea, right? And you tell a few people at the bar. Before you know it, it's gone by email or these days by WhatsApp or something to, 50 different labs all over the world. By the time you've come back, there are about 50 other people thinking about this problem. And so what happens is that it's becoming increasingly harder to find out who made the really key breakthroughs and who did the incremental stuff or who did the sort of less important stuff. And the key breakthroughs may not be the first thing. The first thing might be rather trite or obvious. It might be some other thing that really was the key breakthrough. So it's getting progressively harder. And that's why you'll often hear with various prizes, oh, but so-and-so was left out, or so-and-so was, it should have gone to these two other people. So I do. So what this has done, getting back to your question, sorry, I'm a bit long-winded here. What this has done is that when people do an important piece of work, they don't know if they're going to be sitting in one of those three chairs when the music stops. I think of it as a game of musical chairs with, three chairs left at the end. And so this leads to anxiety. And then, people are jockeying for position and downplaying other people's work and talking up their own work. And it's a kind of unpleasant side effect of science. And, you can't blame scientists. Scientists are human beings and, we want recognition. It's natural, but I think it's caused by the sort of effect of this sort of rule of three, and the fact that the Nobel is so highly regarded. I mean, there are other prizes that pay a lot more money now, but somehow the Nobel has this cachet because of its history, and you sort of feel that if you get the Nobel Prize, you're part of the historical record of how a field has developed. And that's what people want. It's not so much the cash. I mean, the cash is terrific, but that's not the main
thing. There are such lovely questions coming in, and we're going to have to rush through lots of them. But I just wanted to pick up on one thing you said. You talked about sharing information at meetings. How do you know how much information to share? How do you know what's the fine judgment between what to tell everybody, and they go off and scoop you, and what not to tell people? But it's a difficult thing.
Very tricky, and it's worse in some fields than others. My field is one of the worst, and the reason is that I'm in structural biology. If you determine a structure and somebody else determines a structure, they're going to be the same. Okay, so it matters who determined the structure first, because once the structure is revealed, there's if you do the second structure, what are you going to say? This is the first person. Well, there's certain parts that I slightly disagree with. It's not much of a story. So I think, in some field, and that's true in some other areas as well. For example, in high energy physics, when there used to be competition, between big accelerators, if you were the first person to discover a particle, then that was discovered. So I think it depends on various things. But now if you're in some other area of biology where what you do isn't going to be the same as or exactly like what somebody else is doing, then, it leads to more collegiality. So I think it's very much field dependent. And, my rule is that if I don't want to share something, I also won't listen to and try and get information from other people. It has to be a two-way conversation. So if I'm willing to hear about somebody else's progress and what their lab is doing, then I feel obliged to tell them what I'm doing and where we're at. And if it's a straightforward competitor and I don't want to reveal my thing, then I don't want to know about where they are either. So that is sort of where it is in some fields. Other fields are much more collaborative, and particularly if you're complementary in your approaches, then of course you're quite willing to share, because then you learn from each other. So I think in general, science is a mixture, I'm afraid, of collaboration and competition. I know that it's fashionable to say that we should all be nice and collaborate, etc. But human nature being what it is, competition is always going to be part of the equation. It's never going to go away. So it's always going to be this complicated mixture, because that's how life is. Life is full of competition and collaboration.
Okay, now a lovely question from Shweta, who wants to know the answer to a question that I suppose occurs to every young scientist, which is, how do we change this prevailing culture of doing very long hours in the lab? Or should we change it, I suppose?
Well, I think it's related to the problem of competition, okay? In the sense, if you didn't have any competition, then you might not feel that you have to work at breakneck speed all the time, and you might, take it, at a slower pace, right? So part of the reason that people are putting in long hours is twofold. One is they have a fixed term for their fellowship or their grant, and they have to show progress before it's finished in order to get to the next step, whether it's to get a job or to get a grant renewed. So that's a sort of internal pressure. And then the other external pressure is that there are other labs who might be working on very similar things. And, if you're going to get scooped, that's no fun. So you're going to go all out and go forward. My attitude is that you have to take the long view about it. You have to think of science as a marathon and not a sprint. And you have to also realize, if you're working nonstop all the time, you will burn out. You will also not make the best decisions, on a day-to-day basis, because you're tired and you're not thinking about the long term then. So I, have always tried to balance work and life. So for example, I'm not one of these 24/7 scientists. I've always, I had two children. In fact, when I started my biology career, I had a 6-week-old child and a 6-year-old stepdaughter. And, we're moving across from Ohio to California to start my new career. Well, I couldn't just, ignore my family and just, work around the clock. And so I've always had this idea that, you take weekends off as much as possible, maybe not the entire weekend, but a substantial part of it. I've always had hobbies. I've always had outside interests. Even during the middle of the ribosome race, I started learning Spanish in evening classes at the local sixth form college, or secondary school, as they call it. So these are all ways to get away from your work and just do something else. And what I find is, when you do that, you come back to your work with renewed vigor. And sometimes you think of things that you wouldn't think about if you were just worrying about it, but you go off and relax, and suddenly ideas come to you, or you find a way out of some stumbling block. So I would encourage people not to be too narrow and to try and have a good work-life balance.
Mm. And this fits with a question from Cyan, who is interested in what keeps you motivated. Do you ever lose motivation? And if so, how do you get it back?
There are times when I've been sort of depressed because things are not working and they haven't been working for quite a while, and I don't see a way out. Okay, I don't see a way to sort of get around whatever it is that's not working. And it is hard, I have to say. And I think what does help is what I said to the previous question, is to have a work-life balance. So if you're really feeling low, you go off and do something else, take a vacation, go hiking somewhere, and come back. And that often is enough to keep getting you motivated, get you motivated again. But the more important thing is to try and remind yourself, why are you doing this? What's the goal? Why is it interesting? So there must be something there that motivates you to work on this problem. If you don't have that motivation, if you don't think the end result is interesting and that it's all going to be worth it, then you shouldn't be doing it. My view is that you should then find a problem that actually interests you, or you should perhaps think about a career other than a research career in science. In fact, with a training in science, you can do lots and lots of very interesting things. That is one thing I did learn as president of the Royal Society, how many fantastic careers there are outside of doing sort of a narrow research career in science. And so, you can be in public engagement, in journalism, in policy work. There's just lots of other areas. So there are lots of ways to, stay motivated. And if you're not able to stay motivated, it means perhaps the problem isn't interesting enough. And you should either switch problems or perhaps do something else that might interest you.
Still, questions are coming, and I do encourage other people to, if you haven't submitted a question yet and you'd like to ask one, please do write it in the text box and send it through, and it'll arrive on my screen. So on the question of selecting the problem and being interested in it, Bischoff asked the $64,000 question: how do you know if a scientific problem is worth pursuing?
I think you have to feel that it's both interesting and important. And if you feel it and other people don't, well, actually, that's an advantage. Then you're not going to be competing with dozens of people. If it's very obviously interesting and important, fine, but be aware that there'll be hundreds of other people who also realize that it's interesting and important and will be working on the problem. So I would say those are the two really important criteria, which is you have to find it interesting and you have to believe that it's important in some way. Important doesn't necessarily mean it's important for medicine or applications, but it's important for that body of knowledge, in terms of advancing knowledge.
What about the level of challenge? Because the problem you chose was, some would have said it was impossible when you started, or not, if not impossible, improbable that you would manage to succeed. So how difficult should your problem be?
I think you have to, perhaps a rough rule of thumb is, can you accomplish something in 5 years? What could you do in about 5 years' time to make headway on this problem? So remember, with the ribosome, we started working on the structures of small pieces of the ribosome at first. And it's only gradually that, and partly as a result of ideas that I acquired during my sabbatical, that I realized that actually maybe the whole thing was possible because of developments in synchrotrons and X-ray crystallography methods. And so the question is, can you do something in 5 years? And it's interesting you should ask that, because when I tried to persuade Richard Henderson, who was then the director of the LMB, that they should give me a job so that I could come here and work on the structure of the entire ribosome, he asked me, he said, well, how long do you think it's going to take to get to 7 angstroms resolution? Now, 7 angstroms is not an atomic structure. It's just a halfway house where you can start seeing features. And that sort of forced me to think, what are all the things that have to happen to get to 7 angstroms? So that's the kind of thing you should be asking yourself. What can I do in a few years? And is that going to be something worthwhile? Is it going to take the field forward a bit? But there is no magic formula, unfortunately. This is where good mentorship and having a good environment really helps. And it's why, time and again, these great science often gets done in, a certain subset of places. And it's because there are people there who've tackled hard problems, so they know the kind of thinking that goes behind it. They know when a problem is ripe for attack, when it's too difficult or premature, when to change tack, when to abandon the problem. These are all judgment calls. There's no sort of recipe to follow to say, okay, you should abandon it because when this, and this happens. And so you get that sort of judgment by surrounding yourself with people who've all sort of had to tackle that sort of, issue in their own life. And so I think that's what helps. So talking to people actually helps.
And that's something that really comes out from talking to you and other laureates. The idea of serving a sort of an apprenticeship with those who have tackled difficult things before, and really, it's very difficult to be a ready-made scientist, ready to go. You have to spend time, don't you, with people?
Yeah, you do. I'll tell you, there's a crasser way to even express that, and that is the statistics that show that if you've been a student or a postdoc of a Nobel laureate, your chances of winning a Nobel Prize are much higher. Okay, so they worked out these sort of odds, and whether the odds are true or not, you have to ask if it were true. If it's true, why is it true? It's not because the Nobel laureate has some in with the committee and is going to, get you a prize. No, it's because they have done really groundbreaking work in their own lives, and they've had to make this constant decision of should I stick with it, should I abandon it, should I change tack, should I do something else? That's a constant questioning that they've had to do in their lives, and they can sort of give you through mentorship some idea of how that decision making goes on, and also how to choose problems. That's a huge part of science, is how to choose a good problem, and that you learn from mentorship and from colleagues, not just mentors, but the sort of environment around you. And going to meetings helps, where you can see how other people are approaching problems.
Okay, we're rattling through the subjects. Next one, it's a subject that could take up an entire 1-hour conversation very easily. But several of the people are interested to know what your view of the assessment process is, and whether assessing through publications and high impact publications is a fair way of judging people.
It's not a fair way, but it's a common way, and it's an easy way. And no matter how often those of us who are in academies like the Royal Society keep saying, oh, this is a terrible system and we should never do it, the reality is the following. Let's say I publish a paper in Science or Nature. You know how these journals are organized. You get cosmology, astrophysics, high energy physics, solid state, condensed matter physics, then into chemistry, then into molecular biology, then into sort of cell biology, and then systems biology, and then ecology, and so on. So it's a gradation, right? So you would expect that if you publish a paper in Nature or Science, you should be able to understand the paper before yours and the one after yours in the issue, right? Try doing that. And I challenge you to get beyond the abstract, okay? Because it's very quickly degenerates into jargon, and you have no idea, is this paper important or not important, okay? Somebody thought it was important enough to publish in Nature. Who were those people? Whether they were the experts in that particular area's field. So what happens, imagine now you're a on the selection committee for either a fellowship or a faculty recruitment committee at your institution, and you get 200 applications, and you've got one faculty position, right? And your job is to look at these 200 applications and figure out who are the 5 people you're going to shortlist. Now, if you were really conscientious, what you would do is you would read through all of the 200 applications, try to see, had they done interesting work? Did their proposal make sense? Do they have good plans for the future? That's how it should be done. And I have to say, at a few places, I mean, at the LMB, we've often hired people without any papers in cell, nature, or science. And that's because we're familiar with the fields in which they're working in. And so we know what the questions are. But if we didn't know that, then, we would be at a loss for how to evaluate these people. And so what lots of people do is to take the shortcut. They say, well, the editors of these journals have asked the experts in their field, and these experts have said, this is one of the most important, findings in this field and worthy of publication in these journals. So they take it as a proxy. That's the problem, okay? The problem is science has become so specialized that we can't really evaluate without a huge amount of work, even things which are slightly away from our own narrow expertise. How we solve that problem is not clear, okay? We can say we should ignore all these things, but what will happen is you'll get a different kind of journal, and then you'll get a different kind of ranking system. Ultimately, there'll be some other hierarchy that people will look at. And I don't know, honestly, how to get around it. It is a problem.
Thank you very much indeed. So for now, play the game. Manik was obviously very taken by your idea of finding a research field that's your own without too much competition, but then asked the follow-on question, so how do you get somebody to fund a project that is so exclusive and narrow?
Yeah, so you found a field that's your own. Why did you choose that field? And I said, remember, the 2 criteria, it has to be interesting, at least to you, and it has to be important. The importance has to be something you can explain to other people. So it's your job to explain, why is this interesting, and why is it important, and why is it worth funding? That comes with the choice of the problem. So there's no getting around that. You have to be able to make the case. And I have to say, to be fair, we complain about these journals, but very often you'll see in Nature or Science a really oddball paper that you would never have thought was, part of the mainstream, but somehow somebody was working on it, found an interesting finding, and it's published, and convinced the editors this is interesting. And granting agencies are also that way. They're not all looking to fund, stem cell biology or cancer research or structural biology. They will fund unusual science if you make the right case for it.
And a nice follow-on question from Donaka Fitzgerald. Is it possible to say whether there are important areas of science that are just being neglected because of the funding environment?
I think that is certainly true. It's not necessarily because of the funding agencies, but it's because of fads in science. It's among the scientists themselves that we tend to work in areas that we know about, that are fashionable, and going to meetings all the time. If you don't go to meetings at all, that's not good because you're isolated, you don't get critical feedback, you don't get exposure to, lots of different science. But if you go to meetings all the time, that also creates a kind of pack mentality. You learn what the fads are and you're influenced by that, and then you don't feel like doing something totally different because everybody else is doing this sort of thing. So I remember in the 80s, I think transcription factors were all the rage. Every week there'd be a new sort of transcription factor and people would be working on that, and that was like the big thing. And if you weren't working on transcription factors, you were sort of a nobody. Then it became signaling, phosphorylation and kinases and so on. So I think there are these fads that always exist in science, and you have to somehow figure out a path. You can join the fad if you feel you've got what it takes, and why not you, right? So that's fine. But you can also try and carve out your own path.
We've got 5 minutes left. So send in any questions in the last minutes if you wish. Valo wonders, if you were starting out and looking for your research field now, is there anything that tempts you? Do you ever think about that?
I'll tell you a couple of areas that fascinate me, which are probably related. One is, of course, AI and machine learning, and the other is cognitive neuroscience, and possibly cognitive neuroscience looking at all levels, from actual thought processes down to the molecules that enable them. I think they're really big, mysterious questions. How do they work? How much more can we learn from them? So I think, if I were maybe 20 years old today, I would be very tempted by those areas. It isn't to say that what I'm doing now is not interesting or important. Perhaps I'm just sort of jaded. I've been doing it for 30 years or so, and so I'm fascinated by these other areas. But that's, you asked me a question, so that's that's my answer.
That's an interesting answer. But again, I mentioned earlier Francis Crick, another physicist turned biophysicist, who then, in later life, went into cognitive neuroscience. So no temptation to follow in his steps?
No. I joke that sort of neurobiology, consciousness, and the origin of life are sort of the graveyards of Nobel laureates. There are quite a few of them who've gone into them. Partly because I think the problems are so both important and extremely challenging. And so I can see how somebody like Crick, who felt he'd reached the pinnacle of molecular biology in the 60s, and he thought, well, I want to now turn to something that's, completely unknown, the way that molecular biology was unknown in 1950 when Crick started, being a biologist. So I can see that temptation. I think in my case, I feel there are sufficiently interesting problems in translation that I feel I'd rather just continue along those lines. I think if I'd been maybe 40 years old instead of 60 when I was sort of at a similar stage, I might have been tempted to switch fields.
Mm. Yeah, because there must be a great temptation to just the joy of the unexplored nature of consciousness, etc. I remember the sort of light in Don Glaser, a physicist's eyes, of course, when he turned to neuroscience. And he didn't do very much in the field.
Exactly. And in fact, you could argue Crick, at best, tried to define the questions. But you could argue he's not had a big impact on neurobiology, at least not according to many neurobiologists I've spoken to. So you could argue it was tilting at windmills, at a problem that was premature. So, I mean, that may be a harsh judgment, but if you ask, what is Crick known for today? It is about the DNA structure and the subsequent work on the genetic code. I mean, that's really the body of work. 500 years from now, that's what Crick is going to be remembered for. I'm not sure that he's going to be remembered for work on consciousness, unless the fact that he tried to define the problem in some way that people follow up on. Maybe that's still possible, but I would say probably not.
Thank you. Okay, unfortunately, this is the last question from Anna. A lovely question to finish with. What do you think is necessary to be a good mentor to young scientists?
I think the first and foremost is regard them as, first of all, try and remember what it was like to be at their stage. I think once people, become PIs and get into the grind of fundraising and career advancement and so on, they forget what it was like to not know anything or to know very little and to be insecure and so on. Try and remember that and have that empathy for the person. So that's the first thing. The second is, remember, they're not your sort of robots, but rather they're budding young scientists. So your job is to help them develop as scientists, give them pride in their work, give them ownership, which I mentioned before, give them ownership of their problem, let them make mistakes because that's how they'll learn. So I think these are all what I think of as common sense, approaches to mentoring, but they've worked, reasonably well for me. And I think where people sometimes make a mistake is they translate their own anxieties about their grant or their career or their promotion or so, and they transfer their anxieties to the people under them. And that is really the worst thing you can do. So even if you just not do that, you've won half the battle, I'd say.
Thank you very much indeed. And that was such a succinct answer. I'm going to throw one more in that's come from Tugce, and that is, as everybody drowns in the deluge of published work, how do you decide what to read on a daily basis in science?
I'm afraid it's dreadful. It's dreadful. Do not imagine that anyone is going to read your paper except possibly the referees, okay, the reviewers. I think, there is no good solution to the deluge. And eventually, my feeling is that this is going to be done by AI, that we're going to have to rely on intelligent systems to extract information from papers and perhaps point us to key findings, which we can then look for in more detail. Currently, I don't see any alternative. And this is one good thing is going to meetings. At least you get a snapshot of what the community thinks is important, and you can then follow up on that. But it's a very difficult problem.
Going to meetings, a dream for the future now that we all have to meet digitally. But thank you so much, Venki, and thank you to all the kind people from EMBL who have joined us for this session from Heidelberg and elsewhere in Europe. We know how much of your lives is now spent staring to screens, and we really appreciate you with us for this hour. And thank you for all your lovely questions. Thank you to EMBL for hosting us.
And I want to say thanks to Anne. I hadn't seen her for quite some time, and thank her for her very kind introduction. Thank you.
It's nice. It's nice that to reunite old friends. Lovely. Good. Venki, thank you all. Thank you. Thank you, everybody. Bye.